So for the research, the title is Partial Charge Transfer for Adsorbed Chloride on the Go Surface. So for the partial charge transfer, unlike electrochemistry reaction in bulk solution, the charge exchange between electrode and the adsorbate during electrochemical absorption is not necessarily an integer. Here we examine the relationship between the electrode potential and the quantity of charge exchange using computational chemistry. Specifically, we employ density function theory (DFT) calculations at the fixed Fermi level to compute the number of electrons in an electrochemical system. The quantity of charge exchange was found as the difference in the number of electrons between the reactant state, in which the adsorbate is distant from the electrode, and the product state, in which adsorbate is absorbed on the electrode surface. So there are three sets of trials for one set of potential. One is for chloride is absorbed on the electrode. 2. Chloride is far away from electrode, and 3. Only electrode in the solvent model. The qualitative data could not be derived from the calculation. The results could be only used to predict the trend of the charge transfer under different potential. So running the scripts are assigned and run by a program called Slum. When the ironic minimization is going to converge, the data of the number of electrons are recorded and are uploaded into the Excel. And for the potential, for the discussion, for the potential above 0.42 volts versus SHE, the number of electrons in both reactants and product state vary approximately linearly with electrode potential, and the quantity of charge exchange is constant at 0. This corresponds to a partial charge transfer of 0.7 electrons between the electrode and the chloride. However, during PVZ plus minus 0.1 μ, the change in the number of electrons changes drastically, and the graph of partial charge transfer did not show any trend. So for the future, more work is needed to confirm and elucidate the reason for this finding, such as adding more layers, create a vacuum situation inside the solvent model.